Okay, good afternoon. Let us start. Okay, so last class we are discussing about types of neural networks. That is, we are discussing the neural network architectures. So, so basically, we have three types of neural network architectures. These are single layer feed forward architecture, multi-layer feed forward neural network architecture, and recurrent neural network architecture. So in case of a single layer architecture, there will be only one layer. That itself will be the input layer and the output layer. Whereas in a multi-layer architecture, there will be a separate input layer and an output layer. Apart from that, there can be any number of intermediate layers, or these intermediate layers are also called as hidden layers. In case of a recurrent neural network, the output of the neural network will be given as a feedback to the input. So, so this feedback can be connected to anywhere. The output can be either directly given as an input to the first layer, or it can be given as an input to some of the intermediate layer, or an output of a one neuron can be fed back as an input to itself. So there are different styles of constructing this network. So depending on how the feedback is given, based on that, this recurrent neural network architecture was given different name. Like it can be either Hopfield network or Boltzmann machine, like this. Okay, I think we have discussed up to this, right? So now we'll be continuing with this. So like you may have a, so there is the question like, why should we have this many architecture? Why can't we do with just one model of neural network? uh, if you Let us try to answer that question. So why we have different types of neural networks? So let us consider a simple case where we have a single neural network. Okay, that is a single layer neural network. There is only one layer with two inputs. Okay, there is two inputs, right? And this is an activation function. So this is the input layer, and this is the output layer. So this type of model is also called a single layer. Okay, so this output is just added here, or here there is an activation function. It performs sigma wi fi, and it checks whether this value is greater than some threshold or not. So let us consider the threshold as theta. If it is greater than the threshold, it may output as 1, otherwise it will output as 0. So that's the whole idea. So basically here we consider only two inputs, x1 and x2. This third is not an input, it is actually the threshold. The theta is this is the threshold. It is used to check whether the input is, whether whatever the sum of all these things, the I mean the sum of the product of all these things, whether it is greater than theta or not. So that theta is represented here. It is not actually the input, it is the threshold. Okay. Now this thing can be represented like this equation. Whatever the operation that is happening here, it can be represented through this equation. F is equal to, so we can say F is equal to W1 x1. X1 is the first input, W1 is the weight connected with the first input, X2 is the second input, and W2 is the weight connected with the second input. Okay. So this entire thing we have to check whether it is greater than theta or not. So theta also we can bring here in this equation, right? So we can say that theta, for theta also some weight parameter can be added, W naught theta. Okay, but I think you should understand theta is not a part of the input. it is used to, it is a threshold limit, but this can also be written in this equation. Okay, so otherwise you can say that w1, this you can w1 x1 plus w2 x2, it will be either greater than theta or it will be either less than theta. Okay, so it is this, or say for example it is greater than theta. So now we can bring this theta this side, right? By we can say that minus theta, like that we can bring it. Okay, so this sign is not matter, right? So with that idea, it was written like this. Now from this, what we can infer in the sense, basically this is looking like an line equation. If you see this, there is nothing but this is a line equation. So if you say a standard line equation, it is of this form: y is equal to mx plus c. So this is also something like this. So this theta part, you can consider this as this constant c, and basically this is very similar to a line equation. So now if you plot these values, if you assign some values for x1 x2, okay, and if you plot, basically you will get a line, you will get a straight line, something like this, right? Okay, now say for example, whatever the problem that you want to solve, that problem contains these type of data. Say this is the data points of the problem. The data points of the problem that we want to solve is represented through these function. This is one part and this is another part. Okay, this is another part. So this entire problem can be represented through this function. Now if you see, this function is called as a linearly separable function. So if you, there are two functions here. This is, let us call this as function 1, this is function 2. This function 1 is linearly separable. What is meant by linearly separable? Linearly separable means we can easily separate this by using a straight line. That is if the value is above this straight line, then we can say that it is in this category. If the value is below this straight line, then we can say that it is in this category. Say this function is used to differentiate some category, whether it is category A or category B. So now how will you differentiate? This can be easily differentiated by drawing a straight line. So just you have to take any point. So if you say for example this point, I want to know whether it is A or B. I don't know. Let us assume I don't know, and I want to find whether it is A or B. Now you just check whether this point is above this line or below this line. If it is above this line, then you output it as A. Otherwise you output it as B. If you want to check this point, then again check whether it is above it or below it. It is below it. So we will output saying that this point is available in the B category, right? So this is a linearly separable problem. But if you take this problem here, if you see, this problem is represented through this function. So this function contains two categories. So this category 1 is represented like this, and category 2 is represented like this. Now there is no straight line which can separate this perfectly. Okay, for example, if I draw a straight line like this, then there are some points of this function which will fall in the other side. I have drawn a straight line. Okay, so I cannot say that whatever the point you give, so if you give this point and this point is above this straight line, so I will say that it is in A category. But if you give this particular point, this point is below this line, but still it is in A category, it is not in B category. So you cannot always say that if it is below this line, it is B category. So it means that this, in this case, so basically it means that this data points are not linearly separable. The data points corresponding to function f2 is not linearly separable. That is, we cannot separate it by using a straight line. Whereas the data points corresponding to this function, it is linearly separable. The data points corresponding to function 1 is linearly separable, but that is not applicable to function 2. Okay. So why we are discussing all these things? the point is, so if the function is linearly separable, then it can be solved by using a single layer feed forward neural network. Okay, so that's the thing. So if the data points in a function are linearly separable, then it can be solved by using a single layer feed forward neural network. If it is not linearly separable, then you have to go for either multi-layer neural network or recurrent neural network, right? So this is the whole problem. Okay, so could someone summarize what we have discussed so far? Yes. You following or not? Should I repeat? Hmm. Yeah, Kilo, good. So what is meant by linearly separable? Not two function. One function only. The data points within that function is separatable by using a, otherwise it is not linearly separable. Okay, right? So for example, so mainly in machine learning or in neural networks, we want to classify the data. Okay, see normally why we use machine learning, we want to classify whether someone is having this disease or not, whether cancer prediction, whether cancer is there or not, that is what we want to find. Or heart disease prediction, whether heart disease is there or not, or climate, whether it will rain or it won't rain. Okay, whether what is the probability whether the earthquake will happen or it will not happen. So mainly we use it in prediction. So in prediction everything, so for example, if you take the cancer data set, so maybe you may have some data points. See, we are, for simplicity, we are considering two parameters. Only we are taking the, for maybe in x-axis we'll take one parameter, okay, and in y-axis we'll take another parameter. Based on that we are plotting. But actually in reality there may be 10 parameters, 20 parameters, or even 100 parameters. But we cannot plot a graph and visualize those things. Okay, so that we are trying to understand with a two-dimensional data. So that's the thing. Say for example, say these are the data points where say a tumor will create a cancer or not. What is the probability that a tumor will lead to cancer or it will not lead to a cancer? Okay. So for example, these points represent that it is going to create a cancer, right? But that is if that is, say this is the size of the tumor, so this x represents the size of the tumor. Okay, if size is some more than certain things, okay, and say this represents the color of the tumor, this y represents the color of the tumor, how dark color it is. Okay, that is, if it is if the y value is lower, then it lesser, then it means that it is the color is lighter, otherwise it is darker, right? Say for example, there is some other data points for this same what you call tumor, the tumor which the tumor data set, to detect whether it will lead to cancer or not. See, this red points represents even though there is a tumor, it will not lead to cancer. Okay, so this is based on experience. So you may ask, how do we know? It is based on experience. That is, say for example, you have analyzed this many patients, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So this is an individual who is having a tumor. His tumor size is something, so that is represented by this x, and the color is something, but it has not led to cancer. Okay, and this is another patient that he is having a tumor of this particular size and this particular color, which has not led to cancer. So like that we studied some individuals, but these are the individuals, they have tumor and it has led to cancer. Okay, now my question is this data is linearly separable or not? Yeah, where can I draw the line? Yeah, so now I can clearly draw a line and I can say that if the data point is above this, then we can most probably predict that it will lead to cancer, otherwise it won't lead to cancer. Okay, right? But assume that the data points are not like this. Say data, some red is here, okay, some blue points are here. It is something like this. Okay, in this case it is linearly separable or not? Now is it linearly separable or not linearly separable? Pardon me? Somebody is telling something. Now is it linearly separable or not? So now it is not linearly separable. Yeah. So now we want a different function how to separate this. Okay. So so the point is, if the data points are linearly separable, then it can be solved by using a single layer feed forward neural network. If the data points are not linearly separable, then we should go for either multi-layer feed forward neural network, or we should go for recurrent neural network. Okay. So let us try. So this is the whole idea. Now let us try to understand this same concept, linearly separable and non-linearly separable, by using the AND logic and XOR logic. Okay. So if you see the logic for AND, see, this is the logic for AND, which we have already discussed. I think you remember. So this is the AND logic. 0 0 0 0 1 0 1 0 0 1 1 1. Okay. This is XOR logic. 0 0 is 0, 0 1 is 1, 1 0 is 1, 1 1 is 1 0. Okay. That is only when the output is different. Only when the input is different, the output will be 1. If the inputs are same, then the output will be 0 in XOR. So when both the inputs are 0, the output is 0. When both the inputs are 1, then also the output is 0. Okay. So this is the AND logic, and this AND logic can be graphically represented like this. See, this point corresponds to, so we consider this as x1 and this as x2. Say this as x1 and this as x2. So both are 0 means this is here. So in that case the output is 0, right? X1 is 0, x2 is 1, that is this point. Okay, so this is x1 is 0 and x2 is 1. Okay, so it is this point. Here also the output is 0. So this is nothing but 0 1 0 1, right? And so it is this point, we can say this point. Okay. Similarly, next is 1 0. It is x1 is 1 and x2 is 0. So it is this point. In this case 1 0. This is also 0, right? And the last case is 1 1. That is x1 is 1, x2 is also 1. That is this point. Okay. So now these are the 3 points. This is 1 point, this is 1 point, this is 4 points. 1, 2, 3 and 4. Now these data points are linearly separable or not? So what are the outputs? One is 0, another one is 1. So all these are zeros. This alone is 1. Is this linearly separable? Or? Yeah. So there is a straight line. So only this point is 1, remaining all are 0. So this straight line can easily separate it, right? So this AND gate problem, if you see, it is a linearly separable problem. So it means that this can be solved by using a single layer feed forward neural network. Now let us consider the case of XOR. See, this is the truth table for XOR 0 0 0 0 1 1 1 0 1 1 1 0. Now this point is 0 0, okay, which is 0 output. Y is output, right? And this is 0 1. 0 1 is 1, okay, the output is 1 here, and this is 1 0. This is also 1. This is also 1, okay, and this is 1 1. This is 0. Okay, let me use a different color. So now if you see, these points are the one which the green one or the output with 1, and the orange one or the output with 0. So these are the data points. Is there any way to linearly separate this data point? So this is not linearly separable, right? I cannot use a straight line. Is there a, can I draw like this? You can try. So there is no straight line which can separate these data points with output 1 and the data points with output 0, right? So such problems are not solvable by using a single layer feed forward neural network. So now we should go for multi-layer feed forward neural network, right? So that's the whole logic is about, right? So far whatever we have discussed, these are called as binary classification problem. Two classification, it's otherwise called as binary classification. So binary classification means we are saying whether it is yes or no. So here there are only two possible outputs, right? 0 or 1. There is nothing else. So that is called as binary classification. So it's not only with binary classification. So it can be also what you call n-dimensional problem space with multiple level of classification. So then also it's the same case. The same concept can be extended to n classification problem also. So that means if it is not linearly separable, then you should use a multi-layer feed forward neural network or recurrent neural network. So here is one solution for the XOR problem by using a multi-layer feed forward neural network. Okay. So here basically we are using one input layer. See, this is the input layer, one input layer, one output layer, and one hidden layer. This is the input layer, this is the output layer, and this is the hidden layer. Okay. So here we are just giving the input. So this is whatever the value of x1, and this is whatever the value of x2. So both are nothing but it can take either 0 or 1. This can also take either 0 or 1, and these are the weights. So this is the first weight, which is, so you can say that this is W11, okay, and this is W12, this is W21, this is W22, right? These are the weights, okay. So all these weights are assigned with value 1, 1, 1, 1, 1, right? And this activation function, here is an activation function. So you can call this as either activation function or transfer function. In the last lecture we have discussed that this is transfer function, but general term in machine learning or deep learning, the term is actually, it is activation function, okay. So it is just a terminology. You can call it as either activation function or a transfer function. So this activation function or transfer function will contain the threshold limit. That is, if it is more than 0.5, this is going to output 1. Whereas this activation function, this is a neuron, this is a neuron. The neuron here, this neuron will activate if it receives an input which is greater than 0.5. That is the logic. This neuron will activate if it receives an input which is greater than 0.5. If it is greater than 0.5, it will output 1. And this neuron will activate if the if it receives an input which is greater than 1.5. If it is greater than 1.5, it is going to output -1 here, okay. It is going to output -1, right? So that's the whole logic, okay. So now you can see here. So let us assume. See, let us assume the input is 0 0. So if it is 0 0, what will be the value here? what will be the value that is coming as the input to this neuron. So let us call this as n1 and this as n2. Oh, normally what it will be coming? Yeah, 0. So it is basically WIFI, right? Sigma WIFI. So this is, even though the weight is 1, the input is 0, right? So it is both are zeros. So it is 0 into 1. Here also it is 0 into 1. It is 0. So what it is going to output? 0. No, it is 0 only. It is going. Yeah. Only if it is greater than 0.5, it will give 1, right? So this here also it will be, and what it is going to output? This also 0. Yeah. So this both zeros will be combined here, right? So I mean this is also an activation function. So here we are, what we are doing is we are just mm, see, this is weight. I'm sorry, this is a weight. Okay, this minus 1, this 1 is a weight. Okay, this is not output, right? This is a weight. This is a weight for this connection. Okay. Yeah, yeah. Okay. So say this neuron is n1, then this is one of the weight. Okay, and this is another weight. Okay. So in this case, here we get the output. Here the input is 0. Here also the input is 0. So 0 into 1 is what? 0 into 1 is 0, right? And 0 into minus 1 is also 0. Both will be added and it will come here. If this is greater than 0.5, it will result in 1. Otherwise, it will result in 0, right? So here everything is 0, so it will be 0, right? Assume the second case. If it is 0, 1, this is 0, this is 1, right? Now, what will be the input here? I mean, what will come to this activation? Yeah, so 0 into 1 is 0. Yeah, plus 1 into 1 is 1. So, which is greater than 0.5. So, yeah, so basically this will be activated now. This will be activated, right? So what will happen? This 0.5 will be 0.5 will be multiplied with this 1. 0.5 into 1 is 0.5. Similarly, if you see this way, here what will be the input for n2? Y 0. This is 0. This is 1. So 1 into 1 is 1, plus 0 into 1 is 0. So no, no, 1. So 1, right? So so which is so this is 1, right? Okay, so and this is 1.5. Yeah, this will be, yes, so this is 1.5. 1.5 minus 1.5 minus 1. here it is 1 into 1, this is 0 into, so basically it is 1, but this 1 is not greater than 1.5, 1 is less than 1.5, so basically I think this neuron will not fire, right? So if this neuron does not fire, this won't will get activated, only this will be activated. 1.5 into -1. Okay, so let us consider the other case. Say this is 1 and this is 0. If this is 1 and this is 0, then what will be the case? Here for n1 it will be 1. So we can say that this is greater than 1, so this will be activated. So 0.5 into 1, right? Oh, okay, I got it. See, this is greater than, if it is greater than 0.5, this will be activated. But what is the input here? 1. So this 1 will be multiplied this one with this one. So what we will receive here? 1. And this 1 is greater than 0.5? Yes. So what will be the output? 1, right? Okay. So whereas here it is 0, right? So 0 into 1 will be 0 plus 1 into 1. This input will be still 1. This input is still 1, right? But is this 1 is greater than 1.5? No. So will this be activated? This won't be activated. That is the point, right? This function will not be, this neuron will not be triggered. Only this will be triggered, but already you get the output as 1. Okay. This is applicable for 0 1 case also. When it is 0 1 also, only this neuron will fire. This will not fire. Is that clear? When the input is 0 1 also, here for n1 what will be the input? When the input is 0 1, what will be the input for n1? 0 into 1 plus 1 into 1, right? Sigma WXI. So yeah, for this, so it will be 1. So is this 1 is greater than 0.5? 1 is greater than 0.5, right? So this neuron will be activated, and what is this output here? It is producing 1. So 1 into 1 is what? 1, right? Okay. So if both the inputs are 1, let us try to see what is happening. If when both the inputs are 1, so then what will be the input here? It is 1 into 1 plus 1 into 1. So what is the input here? 2. Okay. Is 2 greater than 0.5? So yes, and then 2 into 1 is 2 into 2, and let us see this side also. Okay. So here what will be the input for neuron 2? 2. Is 2 greater than 1.5? So what is 2 into -1? -2. And then this 2 should be added here. That is what? Summation. This is what? So 2 minus 2 is what? Okay, is 0 is greater than 0.5? So what will be the output? 0. Is that is clear? So that is how it works, right? So when the input is 0 1, or when the input is 1 0, which neuron will fire? Let us, out of these two I am asking, out of n1 and n2, which will fire? I mean, which will be activated? Yeah, only this will be activated. This will not be activated, right? Okay. So this is the logic. So the idea is what we are discussing in the sense this is not so here we are using three layers, right? This is input layer and hidden layer and an output layer. Sorry. Okay, fine. So what we are trying to say in the sense, if the data points are not linearly separable, then we should go for neural networks with multiple layers, right? Or we have to go for uh, recurrent neural network. So there is something called as dynamic neural network. Whatever we have discussed so far, these are not dynamic neural network. These are static neural networks. For the neural networks that we have discussed as an example for AND gate and what now we have discussed for XOR gate, all these are not dynamic neural networks. These are static neural network. Why it is called a static neural network in the sense, actually we pre-compute the value for weights. So it means already you have worked out. You have worked out with pen and paper or you have written some program and you have already found the weight. And you have already found the weight and you have fixed the weight here. And this weight is not going to change. Will these weights change? Will this weight will ever change in case of XOR problem or AND problem? It won't change. You have already fixed this weight, and any input you give, it will work properly. It won't create any issues. But this will not be the case with the real world problems. In real world problems, you cannot permanently fix the weight like this. The weight should keep on update depending on the data, right? For example, say that cancer prediction, as of now your dataset may contain 100 data points. So based on these 100 data points, you may identify some weights for these parameters. Say there are four parameters, x1, x2, x3 and x4. Then for each of these four parameters you may fix some weight like w1, w2, w3 and w4. Okay, you in the sense the program may fix some weight. That weight is identified for these 100 data sets. Say tomorrow another 50 data sets were added to this. Now the data set is not same. Previously it was 100, now it is 150. Now accordingly this weight should be adjusted. Okay, accordingly this weight should be adjusted. So so what I'm trying to emphasize in the sense, please try to understand this. The In the real world, the input will keep on come. According to the input, the behavior of the data points will change. When the behavior of the data point changes, the weight should be automatically adjusted. So if you want to adjust the weights automatically, then we cannot do that with static neural network. Then we need a dynamic network. A dynamic network is one which will automatically update its weight, right? So that's what is called as a dynamic neural network, right? So how it is going to update the weight in the sense, see, most of the real world neural networks are dynamic neural network. There is nothing like static neural network, right? If it is a static neural network, then actually we don't need artificial intelligence itself. We can solve using normal programming. The question of AI or machine learning comes because the weight should be adjusted dynamically. Okay, so uh, I will give you with I will try to explain with an example, but how it dynamically adjust in the sense it is actually based on the user input only. Say for example we have some 10 data points. let us assume this way. For a simple case, let us take, yeah, uh, assume that these are uh, data points x and y. Say x is the input and y is the output. Okay, so if x1 is input, then say if x1 is 10, then y1 output should be 25. Say if it is 15, the output should be 35. If it is 25, the output should be 65. Okay? If x is 35, the output should be 75. Okay, like this, there is some data points you have, right? See, I have given only one x for simplicity. It can be multiple x, right? Say, or otherwise, say, let us assume that you have x1 and x2. Okay, so x1, if a, but still y is the output. Y is the output. X1 and x2 are the input. If x1 is 10 and x2 is 20, then the output should be 25. If x1 is 15 and x2 is 10, then the output should be 35. If x1 is 25 and x2 is 5, then the output should be 65. If x1 is 35 and x2 is 7, then the output should be 75. Okay, so these two are the inputs. This is the output, right? Say for example, we have designed some neural network for this. So the inputs are what? X1 and x2, x1 and x2, and there is some weight for connected with this w1 and w2. Okay, and there is some activation function. So this activation function produces the output, right? Okay, say for a given weight, for say assume that x1 is 10 and x2 is 25, it should produce the output what? It should produce an output 25, right? But say that it is producing an output 20. This is producing an output 20, but actual output is what? 25. So now what this neural network will do in the sense, it will calculate the error. How it will calculate the error in the sense, the error will be calculated by subtracting the actual output from the predicted output. Okay. So what is the predicted output here? Predicted output is 20. The actual output is 25. So do the subtraction. 25 minus 20 is 5. So it means that the error is 5. So that will be given as a feedback. That will be given as a feedback, and accordingly these weights will be adjusted. We are not discussing what is the weight now. Say assume that based on that the weight is adjusted. Say some adjustment we are doing in the weight. Say in the next round the output becomes 23, but still there is an error. Now the actual output, the actual output is 23. I mean the actual output should be 25, the predicted output is 23. So again calculate the error. 25 minus 23 is 2. Now the error is 2. So again based on this, what you call this, feedback will be given. Once again weight will be adjusted. So again we are adjusting the weight. But say after adjusting the weight, say now the output is 26. Now the predicted output is 26, actual output is 25. So 25 minus 26, it is minus 1. Now the error is minus 1. Again this will be given as a feedback, right? Once again you adjust. Say after adjusting this time, say the output may be 25.5. So again calculate the error. 25 minus 25.5. Now the error is what? 0.5. Again give this error as a input and adjust the weight. So now if you adjust, now it may be something like this. Now you may get an output 25.05. Okay. So now if you subtract 25.05 minus 25, what is the error now? What is the error? Error is 0.05, which is very small, right? So when it is 0.05 or something like this, you may try to ignore it, right? Or again if you give it as an input, now finally you may get the output as 25. So now if you check 25 minus 25, it is 0. So now you can assume that okay, this is the optimal weight, right? So this is how the neural network learns. So this learning process actually happens. So basically the entire story is updating the weights, identifying the correct weight. So this weight will be, if it is dynamically adjusted like this, based on the actual output and predicted output, if the neural network automatically adjusts its weights, then such neural networks are called as dynamic neural network. So most of the neural network that we are using in deep learning, all those things are dynamic neural networks, right? So the whole logic, it is in finding these correct weights. So whatever we have discussed now, that is explained through this diagram. So this is the input, the whatever x1, x2, all the inputs are given here, and this is the neural network architecture. The whole architecture is represented through this box. You may have any number of neurons, you may have any number of layers, there may be multiple hidden layers, but the entire neural network is this, and this is the output. Now based on the output we calculate the error. So calculating error is what? Just you subtract the actual predicted output from the actual output. Okay. Sometimes we do what is called as, we calculate something called as squared error difference. So in that case, the actual output minus predicted output. So this is actual output. We'll call it as AO minus predicted output. Will take the whole square. Okay. It means we are increasing the difference. Okay. So if the difference is 2, then we are making it 4. That means we are making the linear network to believe that the error is huge. Even if there is a little error, we are doubling the error. Okay. So that the neural network will what do you call, will adjust appropriately with that intention. So we calculate the error, and that is given as a feedback to the neural network. So this feedback, the intention of the feedback is to adjust the weight. So adjust the weight, again calculate the output, again calculate the error. Keep on doing this process. How long you should do this process, that will be decided by the programmer. How long you should do, in the sense, either until the error becomes 0, that is one option, but for some problems the error will not become 0 at all. You may repeat this process for even 1000 times or 10,000 times, or you may do this for whole day, but error may not become 0. So in that case, the programmer may decide that if the error is less than certain value, I will stop, because that much is fine for me. So the programmer may program such a way that if the error is less than 0.5, let us stop the process. Okay, or it depends on the problem. So depending on the problem, certain degree of error can be acceptable, right? You cannot always insist on 0 error, right? In most of the real world problems, that is not possible. For example, when you meet a doctor, say even the doctor is a very famous doctor, say he is a neurologist, okay, so he may give medicines, or he may predict the disease correctly 99% of the times. Maybe 1% he may be missing. Okay, that will happen with human. So why? Because there are outliers, right? So this type of problems also like that only. So we cannot expect that it should always give 100% result. That may not happen. Okay. So this is the whole idea of dynamic neural network. So could someone say what's the difference between static neural network and dynamic neural network? Hmm. Okay. Hmm. Yeah. So we calculate error. How do we calculate the error? Not weight, output. Actual output minus predicted output. What is squared error difference? For simple, actually I told you actual error minus predicted error. But in mostly we do squared error. Okay, we don't just subtract. What we do, in the sense, we perform, say for example, actual output minus predicted output the whole square we do. That is what in the real world we do, right? Why we are doing this square? Why we are doing this square? Yeah, positive value, that is one reason. Another reason is what? Another reason is even though if the error is little, we are telling to the neural network that the error is big. Are you getting? If actual output minus predicted output is say 5, then what is the actual error? Actual error is 5. But what will be actual error minus predicted error the whole square? It is 5 square, right? 5 square is 25. So it means even though the actual error is 5, we are saying that the error is 25. So it means we are exaggerating to the neural network. We are not giving actual error. We are giving that the network is more error, like that we are telling. Okay, so that it will adjust the weights accordingly, right? So that's the point. Okay. Of course, one of the reason is sometimes it may go into negative values. So to make sure that it is not a negative value, so that is also one of the reason why we square it. Okay. So this is the whole concept by which the neural network works. So this is the crux of this whatever we have discussed so far. For linearly separable problems, it can be solved by using single layer feed forward neural network. For non-linearly separable problem, we have to use either multi-layer feed forward network or we have to use dynamic neural networks. Okay, recurrent neural networks or dynamic neural networks. Okay, so that is recurrent neural networks can also be called as dynamic neural networks, or we can say that recurrent neural network comes under the category of dynamic neural networks because there is a feedback. So wherever there is a feedback, that is actually a dynamic neural network. Okay. So this is about neural network architecture. Yeah. Yes. Which diagram? Hmm. See, this is very simple. See here, this is the actual input, right? This is the inputs, right? And this is the neural network architecture. Whatever the neural network we have discussed, like it can be either a single layer neural network or a multi-layer neural network or a recurrent neural network, whatever it may be. And whatever the output comes from the neural network, we see. Let us assume that we know the all the outputs also. So if you say that the x1, x2 and y, these are the input and y is the output. So say if x1 is 2 and x2 is 4, y should be 7. If x1 is 7, x2 is 5, y should be 9. If x1 is 6, x2 is 3, y should be 10. So if this is something like this. Okay. Say for example, for one input, say x1 is 2 and x2 is 4, 2 comma 4. For this, assume that the neural network is giving an output, say 10. Okay. This is the predicted output from the neural network. What is the actual output? What should be the actual output? Yes. This is the actual output. Assume you know 7 is the actual output. So now how much is the error? 3. So how do we calculate? It is actual output minus predicted output. Okay. Actual output is 7, predicted output is 10. So 7 minus 10 is 3. We do the square of that. So it is 3 square, which is 9. So this much error is there, like that the error will be calculated and that will be given as a feedback to the neural network. Based on this error value, the neural network will adjust the weight. Okay, now it will adjust the weight. So this is not only x1, it has, so normally it is what, w1 x1 plus w2 x2. So for every input x1 and x2 there is a weight connected, w1 and w2. So this w1 and w2 will be accordingly updated. So after updating the w1 and w2 for one round, assume that now the output is 8. Okay, now how much the error? Now the actual output is 7. What is the predicted output? 8. 7 minus, yeah, that is 1. Okay. Now this is the new error. Again, this will be given as a feedback, and once again it will update, right? So after updating, say now you are getting an output 9. Now the predicted output is 9. Uh, say or yeah. So now the predicted output is 9, and the actual output is, or let us assume the predicted output is 7.5, and the actual output is 7. So 7 minus 7.5 is minus zero point 0.5. Okay, minus 0.5 the whole square, which is 0.25. Okay, so again you may give this as an input. So again the weight will be adjusted. Now say for example if the output is 7, now the predicted output is 7, actual output is also 7. Now what is the error? Now the error is 0. Now there is no error. Then it means that it has learned. It has learned only for these 2 points. Are you getting? Like that it has to learn for all the points. Is that is clear? Are you getting? Who asked the question? Okay. But why are you traveling? Is it Rupesh? Okay. Fine. So this is the whole logic. So see, but I have told for only one data point, but it should be synchronized for all data points. The weight we are finalizing, no, that weight should be applicable for all data points. Okay. So after doing for first data points, it will tune for the second data point and third data point, like that it will work. For all data points, the weight should work. Okay. So we are not going to find I mean uh, there will be, yeah, we will have multiple weights, but those weights should be tuned with respect to the respective data points. Okay. So this is the idea with dynamic neural network. Okay. So the next topic that we'll be discussing is learning. So learning is actually a core concept in neural network. So basically it is through this concept learning the weights will be adjusted. So what are the different types of learning that is available in neural network? So that's what we are going to discuss next, the concept of learning. So learning is actually basically it is inspired from humans. So as a human we also learn, right? So for example, to a human generally their parents teaches as a child, and then the child learns. Okay. Similarly, the neural network also learns. So how the learning happens, that's what we are going to discuss. So these are the different types of learning we have. So basically, at top level, the learning in neural network can be classified into 3 categories. These are supervised learning, unsupervised learning, and reinforced learning. Again, supervised learning can be, there are two types of supervised learning. One is called as gradient descent, the other one is stochastic. Again, in gradient descent, there are two types, least mean square and backpropagation. In unsupervised, we have these two types, Hebbian and competitive learning. So we'll be focusing more on these techniques, gradient descent, least mean square and backpropagation. We'll be just discussing an introduction to this Hebbian learning and competitive learning. So first let us try to understand what is meant by a supervised learning. See, the previous example what I have told you, that is actually a learning process. Learning is nothing but adjusting weights. How the neural network adjusts the weight. So that process is called as learning. So whatever the example I told you, that actually comes under supervised learning. So I have said that we have some data points and then we see what is the actual output, and then we predict an output and we perform actual output minus predicted output the whole square, and depending on that we will calculate the error, and this error will be given as the input, and again the weights will be adjusted, so on and so forth. That is actually an example for supervised learning. So why it is called supervised learning? Because this type of learning is possible only if you know the actual output. If you don't know the actual output, this is not possible. Right? Only if I know what is the actual output, then only we can use supervised learning. If you don't know the actual output, then the concept of supervised learning is not possible. Okay. So basically supervised learning means you know for all the data points we know what is the input and also what is the output. And initially we assign some dummy weights. So in the entire neural network our objective is to find the weights. So we don't know the weights. Initially we don't know the weights. So we assign some dummy weights and then we run the neural network and we check what is the output. And then we see whatever the output, that is the predicted output, then we check the difference between the actual output and the predicted output and we calculate the error. That will be given as a feedback. Again, based on the feedback, update the weight, again check the error, again update, keep doing this. So this process is called as supervised learning. Why it is called as supervised learning? Because we have something called as training data set. Okay, and in the training data set we know what is input, you know what is output, everything we know. That is you are given with the input and output. So with the actual output we are comparing the predicted output and we are adjusting the weight. Such a mechanism is called as supervised learning. Right? So if you want me to explain further, the logic is that say for example I will take one small neural network. Assume that this is x1, this is x2. Okay, say this is w1, this is w2. Okay, so this is what this is an activation function which is sigma wi xi. Okay, so this is the output we want to find, right? Say for example this is the weight we want to calculate, right? So these are the two inputs x1 and x2 and this is the output y. Let us assume that if x1 is x1 x2, say if x1 is 5 and x2 is 6, the output should be say 10. Okay, so if x1 is 7, x2 is 8, the output should be 12. Let us assume this is two data points alone. This is one data point, this is another data point. Okay, so first our whole concept is what? Identifying the weight. So how will you know what is the weight in the first round? So in the first round we don't know the weight, obviously. So in the first round you have to assume some weight. Okay, when you initially start the neural network for the first time, you should assume some weight. So let us assume the weight as 0.5. Let us assume W1 is 0.5 and also let us assume W2 is 0.5. If W1 is 0.5 and W2 is 0.5, if X1 is 5 and X2 is 6, what will be output here in this activation function, what it will produce? What is not? Yeah, what is that? 5 into 0.5 is 2.5. Okay. 6 into 0.5 is 3. 2.5 plus 3 is 5.5. Okay, this is what predicted output. But what is the actual output? 10. So what is the error? 10 minus 5.5, which is 4.5, right? 4.5. Yeah, what is that? Okay, let us not bother about that. So this 4.5 whole square, that is given as the input here. Okay. So one more thing you should understand. If the error is a positive error, so in this case it is a positive error because 10 minus 5.5 is a 4.5 is a positive number. If it is a positive number, you have to generally increase the weight. Okay. If it is a negative number, you have to decrease the weight. So now should we increase the weight or decrease the weight? Now weight should be increased or decreased? Increased. Okay. So let us assume that we are increasing. Say W1 we are making 0.7. Say W2 also we are making 0.7. Now what will be the output in the next round? Yeah. What is that? Okay. So the output is 7.7, right? So now there is what? 10 minus 7.7. What is that? 10 minus 2.3 squared. Now still is it a positive error or a negative error? So what should happen to W1 and W2? Increased. Okay. So say that we are making both as 0.8. So if it is 0.8, if both are 0.8, then what will be the output? 4 plus 5 into 0.8 plus 6 into 0.8. What is that? 8.8, right? So what is the error now? 10 minus 8.8, what is that? 1.2 whole square. Still it is a positive error. Okay. So both should be in. So say that we are making W1 as 0.9 and W2 also as 0.9. So then what is the case? 5 into 0.9. So 6 into 9. 9.9. Okay. So 9.9 is how much is the error? 0.1. Okay, that is pretty less, right? So either you can stop here. It is so. I mean the difference is very less between the actual output and the predicted output. Okay. So maybe you can either ignore this because the error is now very small, right? Or still if you want to improve, still it is a positive error. So if you now if you increase, say for example, we are making W1 as 1 and also W2 as 1, then what will be the output? Yeah, 11, that is 11 minus 10 minus 11 is minus 1. Okay, which which is a negative error. What it says? Decreased. Okay, so already, so let us assume that let us decrease one weight. So let us keep W1 as 1. Let us keep W1 as 1. Let us make W2 around 0.9. Now what will be the output? 5 plus 6 into 0.9. What is that? 10.4, right? Right? 10. So the actual output is, I mean the predicted output is 10.4. Actual output is 10. So 10.4 is minus 0.4. Right? Still it is negative direction. So still you have to reduce. So this, so already one is 0.9 and one is 1. Okay. So this one, let us make as 0.95. Okay, this is 0.95, this is 0.9. So now what will be that? 0.95 into plus, yeah, 0.9 into 6, 10.15. Okay, so like that the function works, right? Finally it will converge. So convergence, generally we won't get zero error, like how what we get 0.1 or 0.01. At that point we will stop. Okay. So why I told you this in the sense, first initially we have to assume some weight. So that is applicable for all machine learning algorithms. First time the algorithm don't know the weight. Okay, so some minimum weight we will start 0.1 or 0.01, like that we will start. Right? And this type of learning where we know both the output, I mean we know the actual output also, then we can go for supervised learning. If you know the actual output only, you can go for supervised learning, right? So this is something similar to learning with the help of a teacher. Because when you learn with the help of a teacher, what happens? The teacher will ask the question, what is the answer of this? If you say the correct answer, it is fine. Then the teacher will say this. The teacher will acknowledge that it is correct answer. Okay. So then you can ensure that it is correct. If it is not correct, then the teacher will say that it is not correct. It is like this. Then you will understand like how much it is wrong. Then accordingly you will update yourself. So the same thing is happening here. Okay. So somebody is supervising, somebody is guiding. So who is guiding? The actual output is guiding us. The actual output is guiding us, like how far we are away from the actual output. So based on that, the algorithm is learning. So this type of algorithm is called as supervised learning algorithms. Right? The second category of algorithm is called as unsupervised learning algorithm. In case of unsupervised learning algorithm, we don't know what is the actual output. Okay. Because in some real world problem, actually we don't know what is the actual output. You have only data points. You have only data points. We don't know out of that which is which category, which is what category, all those things we don't know. We have only some data points. Now the actual output is not known. Now how will you differentiate? So that is the question. Okay. So this is something like a child is learning by itself without anybody's guidance. Okay, you can say that as an example, right? You can say that a child is learning by itself without anybody's guidance. Okay, but still the child can understand the difference between the things, and the child can categorize the things. Okay, such type of learning is called as unsupervised learning. So then what unsupervised learning does? You may ask this question. So what unsupervised learning does in the sense it performs something called as clustering. Like it says that all these items belong to one category. Okay, like that it will group items together and it will say that whereas these items belong to some other category. Okay, it does not know the name, it does not know the exact name of this category, but it says that all these are similar items. I will call this category A. All these are similar items. I will call this category B. Okay, maybe all these are similar items. All I will call this as category C. So based on the data set features, based on the features of the data set, it will group into different categories. So that type of learning is called as unsupervised learning, right? Okay. So if you want me to give a concrete example, okay. Let us assume that you are writing a machine learning program which will separate orange from apple. Okay. So the input, if the input is the input can be either orange or apple, right? But you are not telling which is orange, which is apple. Okay. So if you are telling to the program this is orange and you learn, like that if you tell, that is called supervised learning. But here you are not telling which is orange, which is apple. You are only giving input. You are giving 100 inputs orange and 100 input apple. Okay. So actually the algorithm does not know the term orange and apple, but whenever you but after say after giving one input, 10 inputs, 20 inputs, or after giving 20, 30 inputs, the algorithm will understand that okay, this first input is different from this input. I mean, you are giving images, the images of the fruit orange and the images of the fruit apple. So the algorithm will start differentiating, and it will understand that this image is different from this image. So all these images it will put into one class. Say it will call it as class A. Okay, and all these apples it may put it in another class, so that is called as class B. It actually don't know that this is orange, this is apple, but it will know that this belongs to a separate class and this belongs to a separate class. Okay, so how it knows? Because the features of this image is different from the features of this image. So based on the features, it classifies. Okay. So could someone say what's the difference between supervised learning and unsupervised learning? Hmm. Yeah. So what the unsupervised learning will do? Yeah. Based on the features, it categorizes. It gives some label like A, B, C. It don't know the actual name. Okay. Fine. Let us stop here for today's session. Okay. So 3 o'clock the quiz 3 will start. Let me take the attendance. 32 Gautam absent. Lohit 79. 348 Sai Abhinav. 351 Rupesh. 269 Bibin. Bibin is absent. 389 Harish. 200 Akilo. 306 Sai Charan. 410. Pardon? Who is that? Okay. So as usual in the previous quiz, how many we had? 20 or 25, not more than that. Hmm. Okay, thank you. I'll share the Google form. And fill it up. 3 o'clock. You can inform others also. Yeah, 3 to 3:20.